The purpose of this lab is to examine the motion of a spring mass system in which the mass swings in an arc while also oscillating on the spring. Newton's second law states that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. The velocity update formula uses the definition of acceleration from Newton's second law to update velocity over a small time step. And to update the object's position, we assume that the velocity is constant over the small time step. Hooke's law describes the restoring force exerted by a spring when it compresses or is stretched. The kinetic energy formula measures how much energy the object has due to its motion. The gravitational potential energy represents the potential energy an object has because of its position in a gravitational field. The spring potential energy is the energy stored in the stretched or compressed spring. The total energy is the sum of these energies, which should remain constant. The main results of this lab show that the simulation captures the essential dynamics and energy behavior of the system, but the lack of exposition data and energy loss in the model cause discrepancies between the model and the observations. Here's a tracker analysis video. System includes the mass, the spring, and the Earth, while the surroundings are everything else. From the video, the initial mass was 0. This is the model Y motion only, and since the mass was released from rest, the initial velocity is 0. And these are the calculations for the period of oscillation, the spring stiffness, and the relaxed length. Tracker software was used to extract the position data from the mass in the video. The position data was copied to a spreadsheet and saved as a CSV file. The starter code on GlowScript was modified to model the motion analyzed in the video. Finally, I inputted the CSV data file into the code and compared the computed motion and the tracker data. For the code, I put the initial conditions, the stiffness constant, and the relaxed length calculated before. To find the spring vector L, the position of the spring's fixed attachment point was subtracted from the position of the mass. Then its unit vector was calculated, and using Hooke's law, the extension of the spring is determined. The kinetic energy, gravitational potential energy, and the spring potential energy were added to get the total energy using the formulas discussed before. In the calculation loop, the initial energies are saved to compute the energy changes after the update. The net force was calculated by adding the spring force and gravitational force. Next, Newton's second law was applied to get the updated velocity and position for each point. In the model, the red ball shows where the mass was observed to be, and the blue ball shows where the computer model predicts where the mass should be. The change in energy versus time graph shows that the blue curve representing the change in kinetic energy is decreasing its amplitude. The exposition versus time graph shows that experimental data clearly had movement in this axis, while for the model, it's constantly at 0, since the simulation only models the Y motion. Finally, the Y position versus time graph shows that both the model and experiment demonstrate oscillations in the Y-axis, and the spring is bouncing as expected. The periods appear reasonably similar, but the model's amplitude is larger than that of the experimental data. Some sources of error could be errors in manually placing tracker markers that can result in small shifts in the observed oscillations. The model also makes ideal assumptions of no release of energy and no air resistance. And finally, the model doesn't account for movement in the x-axis, creating a mismatch with the experimental data. For the discussion, the energy principle is mostly satisfied in the model. This is because ideally the change in total energy in the model should be 0 joules, but the model shows an oscillating change in energy, so the energy principle isn't perfectly satisfied. Using the tracker data, the Y position data estimated a period of 1.524 seconds, and the X position a period of 1.657 seconds. This difference may be a result from energy dissipation but the periods are reasonably consistent and confirm that the mass undergoes motion in both directions. Thank you.